This meeting is being recorded.
Okay.
Hello, everyone.
Okay.
Steve, thanks for muting me earlier. I didn't realize I was on. I was
Okay.
be there.
No problem.
All right, folks. Well, we're going to start in just a minute. Mark's working on sharing. Good job.
Okay, Google.
Beautiful, beautiful. I want to live there.
Hey, Google.
I want to go there. Okay, folks.
Hey,
For just a moment. So let's let everyone join us.
If you're not talking, could you mute, please? Thank you.
Okay, do you just want me to start and introduce myself, Adam?
Hold on just a minute. Let's just wait just one more minute and then
Okay.
we'll get started.
Would it be possible for Mark to turn on his camera so we could see his face as he's talking?
If you like, Mark, if you'd like to be visible to the world, feel free. So welcome to BNUG. It's 7:30, so we'll get started. Welcome to BNUG, everyone. It's great to have you. I do encourage everybody to turn on your camera. We'd love to see you. Steve, if you could rename yourself as you.
I already am.
That's odd.
Can you see me now?
Oh, I see it. There must be another. Oh, that must be another user. Yes, we can see you, Mark. Thank you. Welcome.
Thank you.
Welcome, new people. This is the Boston Network Users Group. We are old. We've been around for 35 years. We hope to be around for the next 35. And we welcome people to join us in our monthly meetings and join us to plan our monthly meetings. We welcome speakers from all walks of life to teach us about computers in the many, many ways computers play a role in our society. And tonight we have, I consider, a very special privilege. So Mark Hanley, I met when he was running a printer research company. And when he retired, he decided to take on a new hobby. And this is it. So I asked Mark if he would come and talk to us about the way astronomy has changed. And it has changed dramatically, apparently. How the astronomy world has changed because of the role that having computational power has brought us. I just wanted to just say a very quick word before Mark begins about Tycho Brahe, a Danish nobleman who, against his parents' wishes and the people of his social class, became a scientist. And he basically took a stick and pointed it at the sky and started measuring where the stars were. No one had ever done this. People have been studying the stars since time immemorial, but no one had ever measured them. He measured them with an accuracy that we measured him with an extraordinary accuracy, 10 times greater than anyone had done so. And it was that laid the groundwork for Kepler's work and for Newton's discovery of the law of gravitation. And so we're now looking, not that many years later, at what some of the fruits of that. So welcome, Mark Hanley. Thanks so much for coming and joining us.
All right, thank you very much, Adam, for that kind introduction. So I'm just going to, I've got about 20 slides. They have a lot of information on them because I thought that you, like me, would be interested by the technical side. And it's got some very nice pictures in it. You use the word astronomy, and you know, I guess as lay people, we all think of astronomers as, you know, just ordinary people looking up at the sky and taking an interest in it and studying it, and that's fair enough. I'm going to talk specifically, however, about astrophotography. So when you look up at the sky, you can do it with your naked eye, obviously. You can look through a telescope with your eye, or you can put a camera at the back of the telescope. I put a camera at the back of the telescope. I have no particular interest in visual astronomy with the eye because the eye is so spectacularly insensitive by comparison to today's CMOS cameras, that it's a totally different experience. There's nothing wrong with that, but I took an interest specifically in astrophotography. So I'm going to tell you what it means to me. I'm going to give you some reference points for understanding how I describe it, and in particular, how I measure it. And I'm going to describe to you, I hope by the end of it, you'll have a good idea why it caught my interest. Adam's right. I retired partly because of age, partly because of health, and partly because of the pandemic. And at the beginning of my retirement, which coincided with the beginning of the pandemic, I bought all this equipment for about $5,000. And then I let it sit there for 2.5 years until Heather, who was on this call, said to me, sell it or use it. So fair enough. I went out and started using it basically from the fall of last year. Now, obviously, I did my research. I wasn't a complete neophyte, but I'd never actually done it before. Now, when we talk about astrophotography, you're talking about the capturing of the image with telescopes and cameras, and that's about, I would say, call it half of the job. And the other half of the job is to take the pictures you take and pass them through some very sophisticated, but happily not very expensive software with which you post-process it. And really, the processing of astrophotographs has nothing to do with ordinary photography, as I will explain. So let me move on to the next slide. Just let's talk a little bit about scale and measurement. When you look out into the sky, you're looking, as it were, from the center of a sphere out into the, if you like to think of it that way, the inner surface of a sphere. So when you do that, as you look north and south, you have a measurement called, in astronomy, declination. And as you look east and west, you have a measurement called right ascension. Right ascension is really a word for the astronomical lines of longitude. We call them right ascension lines, and they're measured in hours. So the first line is hour 1, second line is hour 2, right around the globe until you cover 24 hours. That's how we measure things, and you will see these terms, so it's worth you understanding. Now, the way we measure things, how big they are apparently to our eyes or instruments as we look out, we measure them in terms of degrees. So as you look around the horizon, if you turned around a full circle looking at the horizon, you would be looking through 360 degrees. Now, so you could point to something, say, on the eastern horizon and say that's 90 degrees from north. But within that wouldn't be sufficiently accurate. Within each degree, there are then 60 minutes, and within each minute, there are 60 seconds. Now, just to give you an idea of what that physically looks like, I found this very nice chart on the internet on the top right of the slide, which shows you if you hold your hand out and you look at the tip of your little finger, you're covering about 1 degree of the sky, or 60 arc minutes. 3 fingers is 5 degrees, a fist is 10 degrees, 2 fingers at either side of your hand stretched out is 15 degrees, and tip of your thumb to tip of your little finger stretched out is about 25 degrees. This will become meaningful as we compare the sizes of things. So it's very important you understand the relative sizes of the things I'm looking at. And it's also very important, as I'll explain in a minute, that you understand how faint they are. So the abbreviations for things, obviously, you know the abbreviation for degrees. An arc minute is A dash, and arc second is A double dash. So bear that in mind, and you can, have a copy of these slides and make reference later should it be that interesting to you. Now, I want to show you why I got interested with this next slide in astrophotography. On the right, you have a picture of what the Hubble telescope photographed about 25 years ago of the so-called pillars of creation, which is a nebulous feature within the within the overall Eagle Nebula, which I'll show you where that is on the celestial sphere in a moment. That picture was taken with the Hubble telescope, which obviously was an investment of many billions of dollars, and we were all amazed by it. The picture on the left is actually taken by an amateur in Buenos Aires with a 7-inch backyard refractor, and that refractor cost less than $50,000. And the big enabler of this, and I'll explain what this means in a minute, is the CMOS camera. The extraordinary sensitivity of digital cameras allows this amateur almost to emulate what the Hubble could do. Now, that doesn't mean that the Hubble has no role. The James Webb Telescope can now do things which are thousands of times greater than what the Hubble could do. But still, it's amazing and shocked me. This picture actually comes from an advertisement from the telescope manufacturer in an astronomy magazine published in the US. So that's really, that kind of concept caught my eye. I can't remember how or when, but it did. And I thought, oh my goodness, if you can do that in your backyard, I mean, that's really worth doing. Now, it is not easy to do that, but you can do it. So that just was what inspired me, and I thought you'd be interested to see that really quite extraordinary comparison. And it was not possible 25 years ago to do that. These CMOS cameras have been around, well, they've been around as a technology for 30 years, but they've been accessible, that is to say, economically accessible, for really less than 10 years. What preceded CMOS, by the way, was CCD. And the difference between the two, I'm not going to bother to get into now, but there is a difference. CMOS are more sophisticated than CCDs. Anyway, that's how it began for me. Now, just to show you the scale of what we're looking at so that you get a feel for what we're doing here. In real life, objectively speaking, the height of that feature you see in the picture on the left is 4 to 5 light years. And as you know, light moves at about 186,000 miles per second. So it's a huge, huge, huge feature. So for your information, if you want a comparison, the whole of our solar system has a diameter of about 1.3 thousandths of 1 light year, or in plain old miles, 7.4 billion miles. So this feature you're looking at in the Eagle Nebula I mean, the solar system would be an invisible dot on it, just to give you a sense of scale. And where that feature is, in the middle picture, you can see it's a very small feature within the overall Eagle Nebula. The Eagle Nebula itself is in dimensions, apparent dimensions from the Earth, about 70 arc minutes by 50 arc minutes. And it has a magnitude, that's a brightness of about 6.4. That's right at the limit of what you could see with your naked eye. You basically couldn't see the Eagle Nebula with your naked eye. Even with a telescope, it's very difficult, but that depends on the seeing conditions. So, by the way, that Eagle Nebula, just for your interest, is about 5,700 light years distant from us. Comparison to our galaxy is about 100,000 light years in diameter. So that Eagle Nebula, if you look at the picture on the right, is quite, from our perspective, about 50 degrees north. We are, the Eagle Nebula is quite far south, and it never really rises, if I remember right, much beyond about 30 degrees above the horizon. So if you're on the equator, you'd have a much better view of this. But that's where it is. And it is itself within the celestial sphere, as you can see, a very tiny feature next to the constellation of Ophiuchus. So again, I've put the little finger at the top to remind you what 1 degree is compared to this overall dimension. So this is, I hope, giving you a sense of the scale of what we're trying to look at. So with your backyard telescope, you're really trying to get to some very small things out there within the celestial sphere. So just for fun, I mean, this is a really superfluous slide to what I'm trying to talk about, but I find it interesting, and it's just a point of reference again. Our Milky Way galaxy is the top left, and that is a single galaxy within a group of galaxies. In fact, it's within a wing of a group of galaxies, which is known as Laniakea. And Laniakea borders with the Perseus Pisces galaxy supercluster. And those superclusters are to be found within the overall structure of the broader universe. And this is the pattern on the bottom left of all these galactic structures. If you look all around you in what the visible universe presents to the metaphorical eye, anyway, just out of interest. I mean, the scales, as we all know in astronomy, are hard to grasp, but they are just about graspable, and I find that one interesting.
Mark, can I ask you a question?
Yes.
You're saying that the picture below, the purple network there,
Yep.
that yellowish spot is the Milky Way galaxy?
No. The Milky Way galaxy, top left, is part of Laniakea. Laniakea, bottom right, is next to Perseus Pisces. Those wispy-looking structures, they labeled Laniakea and Perseus Pisces, are clusters of galaxies, and the galaxies tend to cluster in lines and to concentrate in thicker lines. That's what you're looking at there. So those lines represent, if you like, linear groups of galaxies. Now, there are many of those clusters that are next to each other in the overall universe, and that's what you're looking at on the bottom left with the purple structures. So the Milky Way would be a dot within one filament of one larger group of filaments within the overall bottom left-hand picture. Did I explain that at all well?
I'm getting it now. So we're a tiny little part of a very, very, very big thing.
Yes, that's correct. And we think of the solar system as big, and then you've got to remember that, that's a mere 7.4 billion miles, whereas our galaxy is 100,000 light years wide. But the galaxy is within a structure which is, many millions of light years wide, and that is with the overall visible universe. I'm not sure to give you a linear distance, but as you know, we can see back as far as about 12.5 billion years, and the age of the galaxy is thought to be 13.5 billion years. So billion years in that sense would be light years. So it's difficult to describe in a very coherent way, but that's how I would describe it.
Thank you.
Now I want to talk about what goes on with astrophotography. Astrophotography can be either the photography of planets on the moon. Planets on the moon don't frankly interest me. It's a separate discipline. Or it can be photography of what are called deep sky objects. Deep sky objects I'll define more clearly in a minute, but basically galaxies or nebula within our own galaxy. So the point about all these deep sky objects is not being the moon or the planets, is that they're extremely faint. Now let me describe what faintness means. If you stand out in the sun at midday on the equator, the sun is emitting over an area of a square meter about 3.6 billion trillion photons per second. Okay, that's 3.6 to the power of 21. When you take the Eagle Nebula at magnitude, approximately magnitude 6, then that's emitting about 24.7 million photons per second per square meter. Actually, if you look at it with the human iris is much smaller than a square meter, and it has the area that's equivalent to the emission of photons from the Eagle Nebula into your iris of about 500,000 into your human iris. that would be a very small percentage of the number of photons the sun emits. So if you take a very faint object, right at the limit of any kind of visibility of about 20, then that might emit, in some cases, less than 60 photons per second per square meter. By the way, for those of you who don't know, I'm sure you probably all do, but anyway, the magnitude scale is a logarithmic scale, not a linear scale. So if you ask where does the human eye fit in all this as a reference point, you might be able to perceive a nebula at magnitude 6 as a faint patch. But unfortunately, when we say that the nebula has a magnitude of 6, overall it does. But nebulas are spread out in the sky. If you remember, I think the Eagle Nebula is 50 by 70 arc minutes. So you have to divide the overall magnitude by the area. So that brings your actual, you might perceive the overall nebula as a faint patch of light at magnitude 6, but you wouldn't see any features in the nebula because features being smaller than the overall nebula itself, being parts of the surface, would actually emit light at a magnitude of about 14, which is below what the eye could perceive. So the eye could never see the features of a nebula. So, by the way, the minimum human eye perception, you wouldn't see a thing, but you might perceive some kind of sensual flash.
Mark,
Is thought
can I ask
to
a
be
question?
about 90 photons per second at 510 nanometers wavelength. Sorry, you asked the question?
Sorry, you're saying Eagle Nebula is a magnitude of about 6. What would our sun be as a magnitude, and is a larger magnitude more brighter?
That's a good question. One of the slides has that number, and I may be remembering it wrong, but I think it's about -20 or -26. It's on one of the slides later. So if you remembering that that scale is logarithmic, you have to go from +6 to -20 or 26 to see the difference. It's a vast, vast, vast difference. I actually find it easier to compare photons per second per square meter, which is what I've done on this slide, but that's the comparison. So you're talking, when you're trying to capture, now a nebula, well, let's talk about what nebulas are. Okay, what are astrophotography targets? Okay, there are solar system objects, planetary and moon. I'm not going to talk about that. It is a separate discipline. It requires different types of telescopes, and it also requires different kinds of cameras. I won't have the time to explain to you why that is, but basically it has to do with the fact that planets and the moon, first of all, are infinitely brighter than deep sky objects, and secondly, they're moving all the time, which deep sky objects are not. That's why it's a separate discipline to capture them visually. So I'm not really interested in that, and I'm not going to talk about that, and we'd better not get into it because we'll get distracted from what is complex enough topic. Deep sky objects, on the other hand, I can classify them into 6 major categories. There are nebulas, which are basically clouds of gas or molecular clouds. They can be emission or reflection, meaning they can actually generate their own light through ionization, or they can reflect the light of stars around them. Nebulas are all basically the visible ones, are mostly in our own, they are all in our own galaxy, although you can see faint remnants of nebulas in some of the closer galaxies outside our galaxy. That's very exceptional. Most nebulas are within our galaxy. You have ordinary nebulas, then you have planetary nebulas, which are generally the remains of exploding stars. You also have really it's a subcategory of a nebula. You have molecular clouds. Molecular clouds, you also have dust clouds. By the way, molecular clouds and dust clouds are what stars are formed out of. Gravity brings dust and molecular clouds together to a point where they condense into stars, and the pressure becomes so great they ignite fusion, reactions, and that's what a star is. So nebulas are often the, if you like, raw materials of what form stars. Sometimes they are what remains when stars explode, like a planetary nebula, but that doesn't mean that material of a planetary nebula would not, in some cases, be reused and repurposed by gravity into further stars. But some of these particulate clouds are pre-star and some are post-star, if you like. There are also dark nebulas which do not reflect light and do not emit light, but act as, if you like, shadows on the background of stars or other objects out there. Other deep sky objects are galaxies outside our own galaxy. And then there are special star formats and clusters, which are considered objects in their own right. Those all are within our own galaxy as well. So these are the main categories. To give you some idea of the relative size of these, I picked out a nice chart out of one of the manuals I used in learning about astrophotography to give you an idea of relative size. A very large nebula is the North American Nebula there. That's about 3 degrees in diameter if you took a circular measure of it. The Pleiades or Pleiades, which many of you will know, about 1 degree in diameter. That Christmas card I sent you, Adam, with the Andromeda Galaxy that I photographed myself, has if you looked at it in a circular way, it has a diameter of about 2 degrees. A nebula out there near Cygnus, the constellation of Cygnus, known as the Eastern Veil Nebula there, NGC 6995, has the diameter of about 100 minutes. To compare with all that, you've got the moon now, which is about 0.5 degree. You've got Jupiter, which is very bright, but is still very small, at about 40 arc seconds. Actually, the way I've represented Jupiter as a sphere there is bigger than it actually is. It's just really a dot. And then you have galaxies like M81 and M82, have a star cluster like M13, you have a trio of galaxies called the Leo trio. And then you have down there a very small feature like something called the Ring Nebula, which is about 1.5 minutes in diameter. So these are the relative sizes. There are about, as catalogued items, something like 7,000 plus deep sky objects, and about 500 of them are worthwhile amateur targets. People would disagree with that and say there's more, but in reality, you know, it's about 500. If you as an amateur are able to photograph more than about 10 or 20 a year, you're doing very well. And you'll see why in a minute when you understand how long you have to expose your photographs and how many you have to take over how many nights. You'll see that it's quite a long process. So the average amateur telescope field of view is between about 40 and 150 arc minutes. There's that relative magnitudes list I was talking about. So the sun is minus 26.7, the moon is minus 12, Jupiter is minus 2.7, the Andromeda Galaxy, just about visible to the naked eye if the sky is very clear, is 3.44. The Ring Nebula you'd never see with your naked eye is about 8.8. As I say, 6 is about the limit of the human eye. So it's a lot of information to absorb, but they're interesting reference points if you want to look back later and you get a more, if you like, universal sense of what we're trying to do here.
Hey, Mark,
So, yes.
Before you move on to the next slide, I just want to make, I'm getting this now. What you're saying is these magnitudes are, a negative magnitude means bigger, right? Brighter, right?
Yes, that's correct. The bigger the magnitude is a positive number, the fainter it is. And remembering, it's a logarithmic scale. So it's exponential, not linear.
So the sun is hugely brighter than the moon. Not just twice.
Yes, and if you go back to this slide, you can see it's 3.6 billion trillion photons a second compared, in my case, to a nebula of 24 million a second. So yes, it's hugely brighter.
Thank you.
Okay. So looking at nebulas, these are pictures that an amateur could take, typically of nebulas. All of these are within our own galaxy. And you have the Messier 1 object, the Planetary, the Crab Nebula. You got the Flaming Star Nebula, which is this molecular cloud called RCW106. And you can't really see nebulas outside of our own galaxy, but you can as single, rather featureless patches of light. And interestingly enough, in my own photograph on the top right here of the Andromeda Nebula, that little blue patch at the bottom is actually a nebula within the Andromeda Nebula. There are very few you can see like that in other people's galaxies, but there is one just for fun. By the way, are these colors real? You know, it's a bit interesting question. You can never see any of these things with the naked eye, and you certainly aren't going to see features of them, and you're certainly not going to see colors. So are these real colors? Well, you can measure the emissions coming to your telescope, in your camera, by their wavelengths. So we know that these colors are approximately correct. But when it comes to color saturation, relative brightness, or exactly which part of the section of the spectrum you're looking at, that's much less certain. So there's a lot of choice that can be legitimately made as to which colors you choose. And even among professional astronomers within observatories, there are alternative palettes that astronomers choose. And it's very legitimate to make these choices because different colors and saturations reveal different features which you might want to look at. So the question of what is true color is a lot more complex than it is in the real visual photographic world, if you like. And there are, you can't invent things, but there's a lot of latitude. That's what nebulas are. By the way,
before we move on, can I ask another question?
Yes.
About these nebulas. If we were magically transported to be near one of these, like right now, we're many, many light years away from these nebulas, right? Even though they're in our galaxy. If we went through a wormhole or something and we're close, like a light year away, would we be able to see this, like look up and see this in this way, do you think?
Yes, you would, but like any three-dimensional object, you're going to look at it from different perspectives or angles or if you like, positionings. And so you might see the shape of it as being completely different. But yes, you're essentially, you are looking at a three-dimensional object here, and there is some software where they reckon to have measured some of these, and you can sort of fly through them and see that. But so yes, you would see it, but it would look substantially different. It's a bit like if you go near a constellation, if you flew out through the wormhole to a constellation, you'd see the same stars, but you wouldn't see them relatively positioned one to another in the same way.
Do you think there are some people on some other planet somewhere who look up and get to see these spectacular sights?
That's a matter of opinion. I certainly do, yes. That's a fascinating thing. One of the fascinating things, I mean, the first fascinating thing is that you can actually go out and look at these things yourself through your camera and capture them for yourself. That's the first amazing, motivating thing. The second thing is indeed that you look out at the Andromeda Galaxy there, and, depending on your beliefs and opinions, there are people there. Of course, you're looking at those people in that case 1,000 years ago, but nevertheless, there are people there looking up at us and other things, yes. That's one of the mysterious fascinations, at least it is for me. I'm not going to argue it, but I believe so, yes, Alan. So when looking at these galaxies, nebulas, many of these nebulas are emission nebulas. Emission means that stars close to these clouds of gas emit so much powerful radiation that they actually knock electrons out of valence orbits. This is called ionization. And as they knock the electrons out of the valence orbit, energy is released in the form of light or photons. And so it's ionized light. In the case of nearly all nebulas, these three narrow bands called the SII band, the NII band, the H alpha band, sorry, 4 of them, and the O3 band, these are the predominant emission wavelength areas, and you use filters to capture these because you only want to capture that light from the emission nebula, and you want to exclude all the other light, which is extraneous and gets in the way of this extremely faint signal. So you do use filters to capture those pictures that I'm showing you on this slide are basically taken by the use of those filters in those 4 major emission bandwidths or sectional bandwidths there. So just so you're aware of that. So there's, in taking these photographs of nebulas, you need to not only have the camera and the telescope, you need to buy the filters. And some of those filters, by the way, it's very expensive, like $800 each. You don't have to do that. You can buy cheaper versions of them. But anyway, it's part of it. Here's a picture of the galaxies you can see out there with your telescope and your camera. All of this is accessible to amateurs. And these in themselves are beautiful. These have a different motivation for looking at them. I mean, they're beautiful aesthetically, of course, and they're also variegated in color. And there's also a lot of gas and emission from them as well. But you're looking here at the fundamental building blocks of the universe. This is where the other planets are and where the other life forms are, if you believe that. And they're just beautiful in their own right, and they take many, many different forms. So I just thought I'd show you a set of beautiful pictures there. One of those on the bottom left is a picture I took, which is Messier 31 Andromeda. That's a very big feature, by the way. It's relatively easy to photograph, so I don't want to take too much credit. Still, it came out nice, wouldn't you say, Adam?
I definitely agree. So this galaxy has planets and stars both in them?
Yeah, what you're looking at there is everything that's emission of light. There's an agglomeration of light from stars. That's all it is. And where you see those dark bands, those are bands usually of dust, sometimes of gas and molecules, which are obscuring the light. So they're like getting in the way of the light between us and them, but it's within the galaxy. So they're bands of dust. All galaxies have bands of dust like that. One of the interesting things that makes the feature. When you take the picture, these things are very poorly, they're very poorly visible. One of the arts in post-processing the software is to make them visible. And it's a very, very complex. I'm not even really going to get into it today, but it's a skill that's like taking a degree course to be able to manipulate the software, to be able to bring those features out. So for example, if you look at NGC 1365, the bar spiral there, that's a very sophisticated picture. I mean, you can take the picture, but to be able to process out all those features, I couldn't do that on that galaxy. It's going to take me a couple of years before I have the skills to do that. It's incredibly high skill to learn image processing from these very, very faint images you pick up with your telescope. Anyway, they're very beautiful. And that's the other type of DSO that I'm principally interested in. So
Mark, can I make a comment, please?
Yes.
Okay, Adam was saying, are these stars and planets that we're seeing? I would suspect that we are only seeing the stars here because the stars are so much greater than the planets, and the planets are only reflecting light, that the stars are providing an overabundance of light, and we really can't see the planets.
Oh yes, you'd never see a planet, and the reason you'd never see a planet is it's just way too small, and like you say, doesn't emit light. As a matter of fact, many planets have been discovered, and I think nearly all within our own galaxy. So you'd certainly never see them, well, with present technologies, you wouldn't see them in another galaxy, but even within our own galaxy. The reason they are detected is through gravitational variance. They, I think, are in most cases not visible, even to the James Webb Telescope, even to the most powerful telescopes. I think there are very few that are visible as shadows, but mostly they're detectable indirectly through gravitational variance. So even with the most massive investment of technology, you wouldn't see a planet today, even in our own galaxy. Yes, that's correct. Okay, so what about telescopes? There are three formats of telescope, basically. There's a refractor, which is looking straight through lenses. That's technically called a dioptric telescope. There are then reflectors, and it's called Newtonian because Sir Isaac Newton invented it. And these are purely reflective mirrors. And that's called a catoptric telescope. I'm not going to go into the etymology of the Greek, although I do know it, but I'm not getting into it because we don't have time. So there are also, and these have become very popular among amateurs, catadioptric. These are mirrors and lenses together, and they're very compact and very powerful, and they make a lot available for relatively low cost, but they're complex. Me, I like refractors, but if you love bigger apertures, then for the dollars you can spend, you're going to get more aperture out of a catadioptric. But a catadioptric is complex and needs stroking and smoothing and petting and being nice to and lots of adjustment. And I don't want to go there. I just want to go out into the yard and set my telescope and take pictures. So refractors have the benefit that they're simple, but you can't really get above apertures beyond 4 to 5 inches without getting into the tens of thousands of dollars, which I don't want to spend. But with catadioptrics, for a much lower cost, you can get into 8, 10, 12 inches aperture. Aperture is like the god of astronomy when it comes to telescopes, because the wider the aperture, and it's a quadratic relationship, of course, the wider the aperture, the more light you gather, and the more features and the greater the resolution that you can see of something. And usually, to an extent, the faster you can gather the light. Actually, the telescopes preferred by professionals in large-scale observatories are still Newtonian reflectors, but you know that's a highly controlled environment, and the cost is not the same object it is to an amateur. But amateurs do use Newtonian reflectors, but they're bare, they're very big, they're very heavy, and that's a problem when the wind gets up and they're not very stable, and they also need a lot of adjustment. They're also open to the air, which means you get contaminants coming in from outside. And, you know, there are big differences between these types of telescopes. Me, I like refractors. They're pure, they don't require much adjustment. They are quite expensive, but for what I need to do, frankly, I don't need to go, in my opinion, beyond 4 to 5 inches aperture. So if there were other astrophotographers here, we'd all have a big debate about that. And that's one of the fun things about a hobby, isn't it? That everybody sort of, in a friendly way, disagrees. So those are the types of telescopes, and me, I'm a refractor man. Now, if we look at what things cost, at the lowest end of astrophotography, you can take a DSLR, a digital single lens reflex camera, and you can put it on a tripod, and with a nice lens for about $1,000 to $2,000, you can get some pretty nice pictures. And you really can. I mean, even amateurs tend to look down their noses at DSLRs. But if you know what you're doing, you can really get beautiful pictures of the kind you've already looked at on my slides, even with the DSLR, because the DSLRs have the same CMOS image detectors in them that we're using on our big telescope. So it's not to be looked down on when people do that with their cameras. But it's a sort of a different class of thing. What I'm doing is in the middle. That's a picture of my setup, my telescope, my mount, which is an equatorial mount in the middle there, and my tripod. And that usually costs you between 4 and 10. My setup there is about $5,000 to $6,000. And there are things I could add which would bring it up to 10. If you have a home observatory and you've got a sliding roof and you've got a permanent mounting there for your telescope, and you've probably got 2 or 3 telescopes, you're talking about spending $50,000 to $500,000. And there's lots of people who do that. I mean, thousands of people. And you can do that in the northeast of the US. You can go down to New Mexico and do it wherever you are. If you really want to go the digital route, you can actually access other people's remote observatories for a subscription fee and then go really big. I don't know too much about that, but it's an available service and plenty of people do it. The centers for that tend to be New Mexico and southern Spain. So that's not a small thing either. But this is the kind of, gives you a sense of the accessibility of a hobby to amateurs anyway. That's my point here. So focal length and telescopic images, very difficult. People ask, how much does your telescope magnify? But it's not about magnification, it's about focal length. So the longer the focal length, the narrower the field of view, as is represented in these pictures here of the kind of field of view you'd get with a rectangular CMOS detector with a lens at these different focal lengths, 50 millimeters, 70 millimeters, 200 millimeters. So now what you're doing is you're taking each of those images and projecting it onto your detector, your CMOS. And these blue rectangles at the bottom on the left show you the different sizes of detectors that you can buy. I needn't tell you that if you want the big one here, that's very, very expensive indeed. That's several $1,000s. So most people are somewhere in the middle on the scale with their detectors. So you take your sensor, I should call it, and whatever the field of view you're getting with your lens focal length, you're projecting that to the full size of your detector. So the bigger your detector is, the bigger you can detect, you can project your image onto it, sorry. So it's a little bit complex to explain like that, but focal length is everything and determines your field of view. But the longer your focal length, you've got to remember your F number. The higher your F number is, the slower your telescope is. In other words, it takes longer to gather light. So in other words, if you imagine at 50 millimeters here, you're gathering X number of photons per second. If you have a longer focal length at 200 millimeters, and you're only looking at a much smaller section of your 50 millimeter area at 200 millimeters, you're getting far fewer photons per second. Fewer photons per second means the image takes a lot longer to build. So there's a price to be paid for longer focal length. So you basically, you want to maximize your aperture, but you want to minimize your focal length. And you want to get the biggest sensor you can, but most of us don't want to spend thousands and thousands of dollars to do that. So it's quite a complex balance. And I'm not expecting everybody's understood that. It took me 3 months to understand the relationship between the size of my sensor, my focal length, and the speed at which I wanted to gather light. And you'll see the significance of that later on when I show you how many images you have to take. So basically, telescope resolution is another way of looking at things. So how small a feature can you resolve with your telescope? It's a complex thing. You have to take at least 4 factors. You have to take your seeing. Your seeing is a measure of what the maximum resolution is available to you from the sky. And that's all about the interacting layers of the sky causing refraction of light waves coming in from outside the atmosphere. Now that is highly variable. When I go outside and there's no moon and it's a fairly clear night in the winter, generally speaking, I can get a resolution of about 1.8 arc seconds. In other words, I can see a feature down to something as small as 1.8 arc seconds, but not better than that. Then you have as a second feature your mount accuracy. Your mount is what your telescope sits on, and it drives the telescope around following the feature in the sky. And those, according to what you spend on the mount, on these range goes from about $1,000 to about $20,000. According to what you spend, the mount is driving your telescope with more or less accuracy. Again, it's measured in arc seconds. My mount, which cost me $2,000, has an accuracy of about 1 arc second. Then you have the actual limit of your telescope optics, the so-called Dawes and Rayleigh limits. So this is a function of aperture and the optics, the purity of your optics. Again, that is measured in arc seconds, and typically my telescope, which cost me about $2,000, has a limit of about it's about, if I remember right, 1.43 arc seconds. And then you have something called the image scale. Oh God, that gets really complicated. That's the ratio between your scope's resolution and the sensor's resolution. The sensor's resolution is measured in number of pixels per millimeter. You multiply those, you take that ratio. Now you have to take all those 4 features and you have to calculate what's called the root mean square. You've got to square each of those measures, add them together, and then take the square root of the product, and that gives you the resolution of your telescope. That measurement took me about 4 months to understand, and I still forget it. But anyway, this gives you the resolution of your telescope. Resolution is fundamentally different from the magnification or the field of view of your telescope. It says that no matter how good your telescope, no matter what your field of view is, no matter how wonderful it is, there is a maximum limit to the feature you can resolve with your telescope, and this is how it's basically calculated. So we don't need to go into more detail on that, but if you're looking to buy a telescope, for God's sake, you actually have to do this calculation, and no, it's not available on the internet. Parts of it are. People like to talk on very interesting and highly informed websites about parts of the telescope's resolution. Very few people put the whole thing together. Some people do, but it takes you a long time to find it. So anyway, about mounts, your telescope is useless to you unless you spend quite a lot of money on your mount. And there are 2 types of mounts. There's an alt azimuth type of mount, and there's a GEM, or German equatorial mount. And I've tried to represent graphically on the left here why you have to basically have a German equatorial mount, because a German equatorial mount is the only kind of mount which maintains the aspect ratio with which you're looking at an object as your telescope on the mount follows the object as the Earth rotates. So German equatorial mount is what you want. You can work with an alt azimuth, but as you see, you're getting a different aspect of the object you're looking at as time goes by. Now, the software can compensate for that. It's not impossible, but it's just another complexity that you can live without if you possibly can. And German equatorial mounts are where the technology has been invested, and some of them are very accurate indeed. They tend to be very, very heavy. If I pick my telescope up out of my house and take it outside to the yard across some steps, and it's about 10 yards, I'm lifting an object which weighs approximately 70 pounds. And you don't want to trip, not with all that expensive stuff in your arms. I mean, you can take it apart and reassemble it, but that's a pain in its own right, especially when the temperature outside is -10. So I tend to try and carry it all. It's about 70 pounds, and it's not easy to do, but it has to be that heavy in order to maintain stability and to track the object you want with minute precision. So those CMOSs, next piece of technology, these CMOSs are described here basically CMOSs have different resolutions within them. The CMOS one I have is the one in the red circle here. It has 24 million pixels. It has a very small pixel, 2.4 microns wide. Now, pixels can be narrower or wider, and they can be deeper or more shallow. A pixel gathers a photon. The photon within the pixel creates a reaction which turns it into an electron, and the electron is stored within the pixel, and it's then counted digitally into something called an analog to digital unit. Basically that then becomes a signal. The number of the size of the pixel relates to the resolution with which you're taking the picture. The depth of the pixel, or the number of electrons you can gather, relates to the brightness of the signal that you can pick up over time as you make a time-determined exposure. So basically, these pixels this is the new technology. This is what's enabled everything. These CMOS sensors now have little mini lenses over the top of them, which focus the light, and they have come down in price incredibly, mainly driven by the domestic, mainly driven by the consumer photography market. But the same sensors used in digital cameras are available to us as astronomers within special adapted astrophotographic cameras. So you can look at that. Yes.
Ask a question. Are you seriously saying there's a single photon that goes into the pixel? Just one photon?
No, I'm saying that in my pixel, for example, on my camera, on my telescope, each pixel has a capacity of 15,000 electrons, or if you like, 15,000 photons that are then turned into electrons. And according to, if within that capacity, I only gather 5,000, that's a certain brightness level. If I gather 10,000, it's twice as bright.
I see.
But the size, the width of the pixel at 2.4 microns determines the resolution. So you're measuring two things with the CMOS, the resolution and the brightness. And the brightness is the number of photons. The resolution is the width of the pixel within the overall sensor.
We use CMOS to power our BIOSes to our computers because they're extremely low energy. They require only a very small amount of energy to keep them going. So we can put a CMOS battery in a computer. It will last 10 years because it's just giving out a little bit of juice to keep the clock going and a few other things. I'm very curious why this technology also works for this. What it is about complementary metal oxide semiconductors that makes it unusually good for storing these photons when they come in.
I can't answer that. I mean, the way I understand CMOS, and I'm certainly not really qualified to say this, but for what it's worth, my layman's understanding is that it's a description of a manufacturing process. It's not necessarily a description of a functioning applied technology, if you see what I'm saying. So
It's really interesting variant.
Yes, I mean, CMOS is a way of laying down a certain type of semiconductor. In this case, you're laying down what chemically are photodiodes, which may be different from what you're doing with a battery. But it's interesting what you raise. I don't know the answer to it, but yeah.
Thank you.
Okay, so when we look at faint images, we have to take many pictures. So when I took the picture of the Andromeda galaxy, if I remember right, the exposure length of a single picture I took was 300 seconds, or 5 minutes. And I took, if I remember right, 80 exposures, so 80 times 5 minutes. So what I'm doing there is each picture has a lot of photons in it. So if you take many pictures, by having a long exposure, you're gathering more and more photons. And by having multiple long exposures, you're able to stack them all together, and you're able to add them, basically. And so you take very faint images which wouldn't otherwise be visible, and you multiply the signal, essentially. So that's what, in principle, you're doing. However, these things are so faint that there are many other extraneous factors which degrade the image. We have external sources and internal sources. The internal sources are things called, and these are features of the electronics before you ever get to exposing anything. You have something called read noise. That is when you go from photon to electron and you transfer the signal into the IC. Sometimes you get random electrons appearing. That's called read noise. Sometimes, in fact, always really, these CMOS have a degree to greater or lesser extent, according to how much money you spend, of banding. You then have something called amp glow. If you don't want to spend $5,000 on the sensor and you only want to spend $800 like me, sometimes you get something called amp glow, which is like a expanding light from the corner of the image, which is caused by electronics. You also get thermal noise. If your camera becomes hot in the summer, it will cause random electrons to pop off. And the pixel has no way of knowing if that's a signal from a deep space object or if it's just because it got hot. So it gets mixed in there. You also get, just as a sort of a quantum effect of such a sophisticated electronic device, you get random pixel firing or failure. So they either suddenly go, a single pixel will go white or black. You also get nonlinear sensor response curves. In other words, you get a variation in the sensitivity of individual pixels across the whole sensor. Externally, you have light pollution, which might be from moonlight, or it might be from street lights, it's just generally light from around a city. And by the way, you probably read that there's very few places in the world now that don't have light pollution. Light pollution itself creates noise. You get signal noise, you get image train impurities. Now, I want to talk about noise. Noise is the huge enemy we're fighting. I can represent noise with this metaphor on the left. Imagine raindrops falling on paving stone. Imagine that where the raindrops fall, that's the signal from your deep sky object. Where it doesn't fall, that's the noise. So anyway, over time in an exposure, photographic noise looks like that second image there. So basically, noise isn't something from the outside. It's just the randomness of patterns, and it's inherent to nature. It's not a bad thing or a good thing. It's just random signal, okay? Now, if as in that image on the left, you've got a super faint object, and your object is only appearing with occasional photons, like those occasional raindrops, then the non-rained areas or non-signal areas become dominant over the signal areas. So the noise dominates the signal. And if the noise dominates the signal, if you look down to the bottom right here, that's what it looks like. We have the Eagle Nebula here on the right, where you've got less noise, where you've either avoided it or taken it out. You never get rid of it. You can only mitigate it. On the left is where, if you don't mitigate it, this is what the Eagle Nebula would look like. Basically, just looks fuzzy. The only way we can deal with noise is by swamping it. In other words, by taking multiple images and getting more and more signal, or by digital post-processing. Now, swamping is an interesting thing. When you take a picture and you get this thing on the left where you get the raindrops as the signal and the non-raindrop areas as the non-signal, the more pictures you take, the non-signal area represents the square root of the signal. So in other words, if you take more and more pictures and you gather more and more signal, then you can add that signal together, and the noise that's left behind is the square root of that. Now, if you know anything about quadrature, you know that as you increase the signal, the noise as a proportion of the signal in quadrature as the square root becomes less and less. So the more images you take, the less noise you have, basically. And this is the art of astrophotography, to multiply the number of images and reduce the noise, because there is no deep sky object that doesn't have noise in it. You take a single picture of any deep sky object, even if you expose it for 10 minutes, and you will get noise. You have to have multiple exposures to reduce noise. And that's the most fundamental way you do reduce noise. And it's quite magical when you take 10 images and you compare them to 50 images, how suddenly your signal jumps out from behind all the noise. That's what we're fighting here. So this is a sort of a schematic representation of what you're doing when you're stacking images. And what you get is a clearer and clearer image and less apparent noise. So light frame stacking is what we do. Here's a little image of where in the post-processing, we took out, for reasons which are different, you take out some of the stacked images within this circle. You take out more here, and here in the, here in the third circle, you haven't, in the third circle there, you haven't taken out any at all in the bottom left. So you can see here how if you take out some of those stacked images, you get the noise back. So this is a good representation of what stacking really does, what the functionality of it is. This is what it's all about in astrophotography. This means if you want to do this hobby, you have to go out for hours and hours and hours, and you have to have a telescope which highly accurately follows the object around in the heavens as the Earth turns. I mean, you have to have accuracy of like a couple of seconds of arc for over hours and hours and hours. And you actually have to do that, not just with a very accurate mount. You actually have to have secondary technologies like tracking scope, which separately track stars and correct the mount itself. And anyway, you have to do this and take many, many pictures at the same time, all of them of relatively long exposure. So that's what we're doing. This is the representation of the system noise. This is your thermal noise on the left, building up as the temperature goes higher, just random electrons firing off in the pixels. Then you have the sensor banding. This is your amp glow on the top right. Bottom right, you've got dead and live pixels in there that randomly come up. And over on the left, that's what read noise looks like. That is when you're internally within the system converting your photons into electrons and putting them into the ICU, you get random electrons. That's read noise. Then you've got light pollution here. This is so-called Bortle scale represented here, and this is the different degrees of light pollution. It's a scale of 1 to 9, and none of us live in a dark sky site. Where we live on the south shore of Massachusetts, in Norwell, 20 miles south of Boston, we're actually in about 4, suburban rural transition. 4 is actually pretty good. You can see quite a lot. When you get into 5, you're beginning to have problems. When you're 6, you're in Quincy or something, or Braintree. And when you're in Boston, you're in 7. And when you're in 8 or 9, you're in New York City, just forget about it. So on the top left, on the top right there, you can see, you can with software, if you've got overall light pollution right across an image, you can actually extract it. The software is able to detect what is light pollution and what isn't. And you can see the extracted image, the extracted light pollution, you can see it there, it's huge. And the sky, that's the sky glow in the top right. In the bottom right, the sky glow has its own noise. It's a form of light signal, and it also has noise. In other words, places where photons don't strike. And that sky glow is in itself a problem that you have to get rid of with multiple exposures. So you've got 2 sources of pollution from light pollution itself. So then you have image train bias calibration. This is where you're not looking at anything in the sky. You're simply shining a light at the camera, and you take a calibration picture over maybe 1/10 of a second, and it will show you if you have dust motes or whether you have vignetting in there, which is a product of your particular image train before you ever get outside the telescope, and it gives you contouring. If you take a calibration picture like that, the software uses the calibration image to take those features out of the actual pictures you took of the sky. So calibration is like taking pictures of bad stuff within the system and having a reference point and saying, okay, we can detect that within the final images taken, and we're going to take out those bad things. That's why you calibrate. So after you've taken the pictures of the sky, you've then got to take these calibration images, some of which you have to take also at long exposures, some of which not long exposures, and you have to put those into the software, and the software compares all these things and takes out what it knows is bad and what it knows is original signal it leaves behind. So that's the processing. One of the things that goes on in post-processing, I mean, there's a whole list of things that go on. We do color synthesis, we remove the gradient, that's like we take out the light pollution. We do color calibration, that is to say we have star charts where we compare all the charts we photograph, and the star charts will correct the color in my image to be the correct color according to wavelength measured in these catalogs. So you get correct star color. You have something called deconvolution, where you sort of make the image less fuzzy. And most importantly of all, you have the histogram stretch. The histogram stretch is illustrated here. Once you've dealt with all your other calibration issues, you actually have quite a dark image on your computer screen. What you have to do is you have to cut off the, on the histogram of the picture, which is a measure of the number of electrons measured at different levels of brightness. On the left is dark, on the right is bright. And you don't want those non-imaged areas on the right and left. You want to take your dynamic available range, and you want to take where you do have signal in the blue, and you want to extend its dynamic range and get rid of the areas where there isn't signal, and that's called stretching histogram, which is represented over there at the bottom right. And what you get is this beautiful effect. When you stretch the histogram, suddenly your object comes out. It's not quite as simple as I make it sound, but it's quite magical. And this is the most motivating moment once you've taken all your pictures. If you've done it right and you've prepped it well and you stretch your histogram and suddenly this stuff comes out, oh my God, it's just a wonderful, wonderful experience. And there's other things you have to do in post-processing like noise reduction. You can enhance structures and contrast. You can reduce and remove stars. You can affect color saturation and many other things. And believe me, I'm not kidding you. It's a whole degree course to learn this and do it right. Thank God the software is available, because there are amateurs interested in this area who are also some of the world's greatest software engineers, and they've written this wonderful stuff, and other amateurs have come in and added to it, and it's all available for like maybe less than $500. And you have a permanent subscription to it. It's just a whole wonderful phenomenon. So that's what goes on. These are some of my own images compared to what you're able to do with my equipment if you knew what you were doing in post-processing. These are pretty poor images. But anyway, I'm not ashamed of them. They're fun. This is where I am. I've only been doing this for 6 months. These are some galaxies, some nebulas, and that's what I've done so far. And it's fun. I've got a better example here. This is what I did 3 weeks ago. On the left is a picture of my screen on my iPad of images I'm taking as I take them. So that's a single image of about 150 seconds. And I'm sitting in my warm living room next to Heather, and I'm looking at these pictures, each one as they come through, checking there's no clouds, and checking that everything's running okay, that the stars aren't creating nasty cracks. And I'm watching that, and that's the basic first image. That's a hydrogen alpha filter image. I then process it through, I've got 30 pre-processed 300-second light frames with this image in the middle. And the image on the right is about my best effort yet of anything, where I have actually taken 150-second images. I took the stars out, processed my nebula image, and then put the stars back after I'd done some things to them to render them less bright and less foreground light. And that image on the right of the Rosette Nebula, those are probably accurate colors as opposed to the red image, which aren't, but these are probably close to the actual wavelengths of the emission spectrums coming to my telescope. That's, for me, a pretty good image, and it's about 2/3 of the way to what it should be. Just to show you what it could be, these are professional images, well, not professional, but these are images of astrophotographers who are at professional level, who really do a wonderful job. This is what I aspire to and what you could do. This is a good image to take because the Rosette Nebula is a particularly large image and it is visible at this time of year. And it has some very beautiful features in it, including these shadow-like features of dust trails across them. It is a very big image, so it's available to my kind of wide-angle telescope. So that's what it looks like. And that particular image on the right is a 6.5-hour total exposure. It's actually multiple exposures, but the total time taken with all the exposures is 6.5 hours. And that's the so-called Hubble palette, because that was the palette chosen for the Hubble telescope in assigning colors to the different filters. So that's what I aspire to do. And this picture in my last slide
Mark,
comes from James Webb telescope.
can I ask one question about the previous slide?
Yes. I'm done now. So please ask away.
What is the pink? What are these pink things that look like little planets? They're not planets, right? All these little pink round things in the.
Oh, the pink round things. So everything that is a point source of light is a star.
So those are stars.
They're all stars, and some of them are stars in the Milky Way between us and the nebula, and some of them are stars near the nebula. Some of those bright stars in the middle are actually within the nebula and are illuminating parts of the nebula. But I don't know enough to tell you which are which. But basically, all point sources are stars.
Thank you.
I might add to that, Adam, there are no planets visible in any of the pictures he's shown. You
No.
can't see any planets because they're too small. I would also think some of those point lights may also be other galaxies. Could I be right on that, Mark?
Well, it's possible that you're absolutely right to say that, and it may be true, and I don't know. Most of these points are stars, in fact, because whatever you tend to look at, you're going to be looking through some kind of field of stars within our own galaxy. If you look straight at the middle of our galaxy, you're going to see huge numbers of stars. This is why sometimes you have to post-process the stars out, because there's simply too many. But if you look to the side of our galaxy, if you look upwards or downwards from our galaxy, then you get less stars. But most stars you see are within our own galaxy, and they are stars. But you're quite right. If you see something which has an elongated shape where other point sources are not elongated, that would be a galaxy, for example. And sometimes it's very obvious. Sometimes it's not very obvious, but yes, you're basically correct. So that's it.
I would also suspect, and I'm going to be just kind of guessing here. If you took that picture on the right and you had the ability to maintain the resolution, and you extended it so that it was a picture that extended from say, Boston to Chicago, then I imagine that a planet would be like a grain of sand in about the right size, were it to be visible.
I don't know to tell you. I mean, it's that kind of relationship for sure. That's the best I can say. I mean, I don't know the actual scale. There's one thing you have to understand here. Although the stars look like they're different sizes here, it's actually an optical illusion. It's because some of them are brighter than others, and they create a larger image on the CMOS within the pixels. In reality, there is no telescope, not even an observatory telescope, which can see any star as a disk. All stars, viewed with any telescope, are simply points of light. So I think that is worth saying, in relation to your scale question about planets. So even these stars, although they look pretty at different sizes and aesthetically it's very pleasing, it's actually an optical illusion. They're all points of light. And a star is, in most cases, most stars are very much bigger than planets. So that gives you a sense. I mean, you just would not ever, I think even at the scale you describe, it might be difficult to see a planet, but I don't actually know. Mike, if you're still listening, Mike is a renowned mathematician, and it's the kind of measurement that he would take pleasure in making. And if he and I could work together on that, we could send you back an answer on that for the group. Mike?
Is Mike here? I think he's not, I'm not seeing him on the list.
Okay, maybe he's had to go and get his dinner, but I'll ask him.
Yeah, that would be great. I'd be so interested to know these relationships between a planet and a star.
You guys, that's always so interesting when you get a new audience, what the point of interest is. You guys, you're all real planet guys.
Well, another thing to consider, Mark, maybe you said this, is that those stars may seem larger because they give off more light, and they may seem larger because they're closer to the camera.
It doesn't matter how close a star is other than the sun. You cannot resolve it to a disk.
Really? Any star, even the closest star?
That's my understanding, yes. I'm going to make, because I'm not really an expert at all, I'm going to make an exception for stars within, let's say, 50 light years. But certainly beyond that, you won't resolve them to a disk. And I believe within that you can't. But again, I'd have to check that.
So
The vast majority of stars you'd ever see in a telescope, you cannot resolve them to a disk. You can resolve them to an apparent disk. It's called an airy disk. And airy is not as in, light and fluffy. It's the name of an English astronomer of the 19th century. The airy disk represents the diffraction limits of the optics of the telescope. And it's basically a blur effect. So you will see a disk, but it's not the disk of the star, it's the disk of the refraction limitation of any telescope.
So for all we know, stars are like wacky shapes. Like they.
Oh, no. We know what size they are. No, we know from other measurements what their diameter and size is. That's not the issue. I'm just saying you can't visually see it.
Uh-huh.
We know very well the individual size of all these stars. I mean, you can. I'm not expert enough to tell you, but I mean, I'm sort of dangerous on that. But there are, even to laymen, graspable methods by which the diameter of stars are measured.
Mm-hmm.
So anyway, that is the end of my presentation. I hope it's given you a fun flavor of astrophotography.
Yes, we had one more slide, right?
No, that was it. Yes, I just show you this. This is the fun. This is a picture taken by the James Webb Telescope, which is infinitely higher performance than the Hubble. And this is a beautiful view. I mean, these pictures just get more and more beautiful. This is why I do it. This is a detail of something called the Eastern Veil Nebula, which is highly visible from our latitude at 50 degrees, generally visible in the summer in the constellation of Cygnus. And this is a huge, wide, actually there's a representation of part of it on one of my earlier slides to give you the relative size. It's a very large nebula. And when you get close to it with a highly resolved telescope like the James Webb, this is what you see. It's utterly, utterly beautiful. I mean, you're probably looking, I don't know what the measure is, you're probably looking even in this detail here at a feature which is probably 5 light years wide. I mean, I don't know, it's huge, but maybe bigger than that. But this is what you see. It's just utterly, utterly beautiful. There's nothing like this anywhere. So I'm speechless. Thank God for your sake that I am.
Now, Adam, I think you said something earlier that we are looking at the stars and we are looking at other stars and maybe planets there. And, you know, I bet you there's some planets where they're looking at us. From those planets, they're looking and they're seeing us. Some people might be concerned that those people, because there are people on some of those planets that might have military objectives and want to send missiles or something of that sort towards us. However, I know from for a fact that they won't fire those until they see the whites of our eyes. So we're safe.
I was wondering why you were bypassing the science, but I realized it was for the sake of wit.
Well, we're halfway there, halfway. Okay.
Very good. All right. Well, anyway, that's my little story. I hope you enjoyed it. I love it.
Thank you so much, Mark. This is extremely interesting. Does anyone have some additional questions? People here.
I'm interested in the mount that you're using. You kind of went over that fairly quickly. You have a fairly decent mount. You can go back to the different. Yes, it's fairly large. It's almost as big as a telescope. But the importance for that, just to emphasize, and maybe you want to go into that, the importance of that is to compensate for the fact that the Earth is moving.
Yes, it's not just that. I mean, obviously, you have to track. We're taking long exposures and many of them. So you have to maintain stasis between the objective of the telescope and the object you're looking at. So to do that, you have to the telescope has to track with the motion of the Earth. And it has to do that with massive accuracy because of these long exposures. You know, an inaccuracy of 1 arc second is going to cause blur and star tracking. You know, a star will turn from a point to a line. So the mount is a very essential part of the technology. First of all, it has to be very solid and heavy. It is. Secondly, it has to have a very accurate mechanism within it. That's why none of them cost less than $1,000. Mine costs $2,000, and you can easily spend $20,000. And actually, if you look on top of my telescope, you see there's a secondary scope there?
Yeah.
That secondary scope is a separate telescope with a separate camera on the back, which hooks onto a star. It doesn't matter what star. Hooks onto any star that's visible. And it tracks whether that star stays static within its field of view. If it begins to track away from its original position within the field of view, the camera there sends a digital signal to the mount, correcting the mount's path of travel according to the measure that the tracking scope took. And it actually is essential when you get beyond 30-second exposure length to have this secondary technology correcting even the very expensive and very accurate mount. So I'm actually double correcting now.
How does the mount know what to do without that? Does it have some other tracking device inside it?
Well, the mount does something called plate correction, and the mount has within it a memory of all the stars. So whatever it sees in the sky, it can orient itself to that. So you have to align the telescope before you begin imaging when you go out every night. You have to polar align it. Polar aligning it means you've got to, you see how the whole telescope is angled up towards a certain angle in the sky? Mm-hmm. Well, essentially it's angled to close to the pole star. Now, the telescope, before you start imaging, looks at the sky and says, aha, that's where I am. Then I tell it through my iPad, oh, please, Mr. Telescope, now I've aligned you, please go to the Rosette Nebula site. And it knows, relative to where it's pointing, where it has to go to find the Rosette Nebula. And once it's at the Rosette Nebula, it knows how to keep tracking with the Rosette Nebula as the Earth moves. That's a computer inside the mount and a vast database inside the mount, and I'm reading all this by Wi-Fi on my iPad. And there's also another little computer inside a box underneath the tripod called a Raspberry Pi, which is a description of a certain processor format. And that does all the local processing of all this data and signals from the telescope and sends it by Wi-Fi to my iPad. And so that's basically what's going on. So I'm in real-time control of the telescope all the time. But there's a computer telling the telescope where to go after I've given it the input. So it's automated. I don't have to do anything.
When you set up the telescope, do you have to tell it latitude, longitude, where its direction it's facing and so forth?
No, all you got to do is align the telescope with a given star, and the computer inside the mount works out where it is. And then everything follows from that as to where you want to point the telescope. You give it instructions to go to something else. It knows relative to where it is, how to go there, and it knows how to stay there. Does that answer your question?
Not quite. So you take your telescope in from the house, you go outside, you set it on the ground. You turn it on and it automatically figures out where it's aiming. Does it automatically? It does. So you set it up and you aim it to a certain spot in the sky. It doesn't matter where you're aiming it. Maybe you're 10 degrees off north and up of an elevation of 35 degrees. You just aim it there and you turn it on and it'll figure out based upon the stars it sees.
Yeah, that's what's called plate solving. It plate solves itself. Plate solving is an old-fashioned term from the 19th century saying that this is the stars we took a picture of with the plate, and this tells us where the telescope's pointing. It's just digitized.
And it's based upon the fact that the stars are kind of like the value of pi in that they're distributed in such a way so that if you get to see a part of the sky, you can tell exactly what part of the sky you're looking at.
Yeah, the stars are, for the purposes of observation, the stars are static relative to one another. The only thing which isn't static is the Earth.
Yes.
That, by the way, is why planetary and lunar astrophotography is a totally different discipline, because they are not static.
You're right, they're running around. The telescope that you have there in the picture in the middle, is the telescope, the mount, is the mount looking through the telescope? So does the mount get the image from the telescope that it uses to do this?
Yeah, you see at the back of the telescope, there's a sort of a red bit right at the back of the telescope.
Yeah.
That's the camera. The camera has a cable which goes to the Raspberry Pi. The Raspberry Pi is a little computer in a red box, and that in turn has a cable running back up to the mount. So the telescope says to the Raspberry Pi, "Hi, this is what I'm seeing." And the Raspberry Pi says, "Oh, thanks. Let me tell the mount." And the mount says, "Oh, great. Let me compare that with where I think I am. Oh, I see where I am. Okay." And then I say to the mount, through my Wi-Fi, I say, "Oh, Mr. Mount, look, thanks. I'm glad you've told me you know where you are. That's great. Now, I want you to go over there, the other side of the sky." And the mount says, "Oh yeah, I know what you want." So, and then it slews in two axes to what I want to see. And when it gets there, the mount says, looks at it and says, "Is this what I think it is?" And it does another plate solve. And if it is what it thinks it is, it reports back to me and says, "Okay, I'm there. I acknowledge that I found the thing and I'm accurately there." And I can actually see a picture of what it's seeing at that point. I can do a preview. So if it's a visible object, I can check that it is seeing what it's seeing. And even if it's not a visible object, it will show me a virtual representation of what it thinks it's looking at, what it actually is looking at. And I can see all that on my iPad. And then
So
when we check that it's all doing what it's all supposed to be doing, I then start the imaging on my iPad. I go to a different subroutine and I say auto run, and it starts taking the pictures. And then I watch the pictures coming through.
So it's automatically a a predetermined map that the software knows of the whole entire sky, then you just tell exactly, you pinpoint, tell it where to go?
Yeah,
Or
these
what?
mounts are sold with databases within them. That's correct.
Do you upgrade them from time to time, or they're fixed?
Well, I mean, no, because there's such a fund of knowledge. There's tens of thousands of times more data in there than I would ever need.
Yeah. And
I mean, it might from time to time, for all I know, be automatically upgrading the catalogs. I mean, the catalogs, I suppose, do get upgraded, but I mean, the catalogs are getting upgraded with the kind of data that the James Webb needs, but I don't need, you know.
Yeah. In the story of Newton's discoveries, he made calculations based on measurements of the moon, and the math didn't work right. And so he refused to publish his results for 5 years. And then it turned out that the astronomers had given him the wrong data. So when the right data came out, it turns out his calculations were right. So,
Well, there are stories today of people who've found things as amateurs that the professional astronomers don't, and there's a very good reason. If you imagine, you know, Mount Paloma or Maui in Hawaii, all these places with these huge, vast telescopes, or Chile, I mean, they only have limited time to look at limited things. They can't be looking at all things all the time, and the celestial sphere is vast. So as a matter of fact, because there's tens of thousands, perhaps hundreds of thousands of people, amateurs looking at the sky, it's quite statistically credible to say that someone among hundreds of thousands is going to see something that the professional observatory didn't see. Yes.
yeah, that makes total sense. Before we wrap up, I just wanted to ask a few questions about the software, because the software seems to be at the heart of our ability to do this. Could you just give us a brief glimpse of the I'm curious about, we're all business people here, so I'm curious about the industrial world of the software. Is it mostly just people who love astronomy who've created the software and they charge for it, or is it a big business?
Well, there's two types of software. The stuff we just were talking about, the catalogs, that's kind of mostly public domain stuff, largely because it's been gathered with public money, and it's just available. And I mean, it's available in higher detail than you ever want, actually. But you can get simplified versions, and that's just available. And that's really from institutions, universities, and government. The software I actually use, there are two types of software. One is the functional control software, which drives the telescope. That comes with the little Raspberry Pi box that you buy, and it's configured to work with most external hardware, like my telescope, my mount, etc. So that's one type of software. That costs $500, but that you're paying mostly for hardware, but it comes with the software, and you install that on your iPad. That controls the equipment you're looking at in the middle there. The most important software, however, isn't that, it's the post-processing software. So in the post-processing world, that's when you've taken your images and you have to do all the calibration and the adjustment. And it's almost an art what you can do. There are a handful of programs which are comprehensive with multiple subroutines. The most famous one is called PixInsight. PixInsight, I'm not sure, it's like a collaborative of people who are obviously top-range software engineers who must have come from the academic world of astrophysics. I mean, there's nowhere else they could have come from, and who understand in you know, PhD level depth about imaging. And they seem to have got together as a collaborative and written the software. And and they don't obviously do it for money. You pay to have access to that software for eternity. You pay less than $300. I mean, it's ridiculous. And it's the most sophisticated. I mean, my MacBook Pro with 32 megabytes of gigabytes of RAM can barely handle it. It's that sophisticated. It can actually handle it, but they also, then there's a group of users who've written subroutines within the software and who put it back to the group and had it sort of stamped with approval and accepted. And you can obtain those subroutines, which enable you not to have to reinvent the wheel in doing certain sophisticated things. In other words, it's like macros for the software. So that's it seems I can only call it a collaborative. I'm not aware that it's affiliated to any institution, and it's sort of, in a simple beginner's way, it's commercial. You do pay for it, and they do obviously benefit from that, but it's not really a business. So there's that, and there are also, at a third level, there are individuals who, I mean, you can use also, by the way, Photoshop for a lot of the post-processing. But and there's competitors to Fix Insight, but there are also individuals who've written very interesting specific subroutines that deal, say, with noise or with color saturation, or separate routines. I mean, you can take your choice, and I think in the end, what people use tends to be what they started with. I mean, I did months and months of research, and I kept seeing statistically the term Pix Insight more than any other. So I bought Pix Insight. I mean, it works like that, you know.
Thank you.
Mark or Adam, are you familiar with with an application called Skyview Lite?
Someone was just telling me about this today.
Yeah, it's as follows: SKYVIEW Lite, LITE. It's a free application on my iPhone.
Yeah.
When you run
Well,
this,
you can. That's a very good point. I should have mentioned there's another application that all the amateurs use called Stellarium. And it's similar to what you're talking about. Stellarium is one I use. Stellarium, you can use it on your iPhone, you can look at the sky, there's Lord and stuff, but you can also put it on your PC, and it will show you for any given time of year what you can see, and it will give you all the details of the objects, and you can specify objects, and it'll flew to it.
can you see what I'm showing right now?
Just a little bit.
Okay, it's showing.
We see your chandelier, Steve.
You do. Okay.
Yes, it's right above the galactic nebula.
Okay. Well, the point I'm trying to make is that with this, you can point it to the sky, and it will show you. It'll look and see the stars in the sky and tell you what they are, and the planets and tell you what they are, and the constellations. It's for a free program, it's fantastic.
Yes, there's a handful of those. The one I use is Stellarium, and it's not just fun. The Stellarium one, for me, I wouldn't be able to go out at night and know what I should choose as an object, and when I can look at it, and what it's near, and what the magnitude is, all those things I need to know. If I didn't have Stellarium, that would be incredibly difficult to know.
This is all just astonishing. I just find this really astonishing and delightful that we can.
Me too.
Yeah. Mark, thanks so much for sharing this with us. I really appreciate it.
Yes, thank you.
My great pleasure, and thank you for the privilege of being able to speak to the group. I never thought I'd be doing that, but I hope you got anyway a flavor of what a wonder and a pleasure it all is.
Very much so. And what I'll do is when we make the video of this, we'll also upload, if it's okay with you, Mark, we'll put your slides up on the website so people can download that.
Absolutely.
Great, thank you so much.
All right, thank you all. I hope to see you again in the group.
Yeah, it's great to have you, and looking forward to more. Have a great night, everybody. Thanks so much for joining us.
Thank you, bye.
Good night, everyone. Have a great month, everybody.
It's working out so far.